So for everyone tuning into the recording now, I'm gonna say something about G equivariant stable stems for some finite group G. And there's various ways that you might try to approach this. For instance, you might say, try an atom spectral sequence approach, which is, well, we know some things for the group C2, and as Process Doc just showed, you can try to say things for other groups, but it's gonna get a little bit scary. However, I want to talk about more of a kind of chromatic approach to getting at these stable stems. Now, I'm not going to give kind of the whole background review of chromatic homotopy theory, but because chromatic homotopy theory brings to mind a lot of different things. For instance, maybe most famously are potency periodicity theorems. But this talk is not going to be about anything nearly so fancy. I just want to extract one small piece of this story, namely the part where chromatic homotopy theory is telling us that the sphere is kind of built from these simpler pieces, the K-and local spheres. And of course, when I say built from, it's built from these in a non-trivial way. What's really going on is that you have the chromatic tower, say the P local sphere is the limit of its Ln localizations, and the Kn local sphere is what comes up when you try to go from the Ln-1 localization to the Ln localization. But for this talk, that sort of gluing is not really going to be playing a role. I'm going to be basically ignoring that gluing because, well, these Kn local spheres already receive maps from the sphere spectrum. They're already giving a lot of information. They're detecting a lot of the patterns that you see in stable stems. So it's one part of the story, but of course an important part of the story is that you don't just have these Kn local spheres, which wouldn't really tell you anything, but rather you have some methods for trying to understand the Kn local sphere. Many coming from the fact that, well, the Kn local sphere is the homotopy fixed point spectrum of Morava E theory with respect to its action by the Morava stabilizer group. And this gives a number of things for you. One thing it tells you is it gives you some other important spectra to look at, namely the fixed point spectra of Morava E theory with respect to various subgroups of the Morava stabilizer group. These are generally going to be a lot easier to get at than the Kn local sphere itself, but they're still going to be kind of very rich objects, detect a lot of good information about how stable stems are behaving. And well, the fact that you have this homotopy fixed point formula means that you have various tools along the lines of, say, homotopy fixed point spectral sequences and other resolution methods for getting at these. Now, so this is all kind of the classical story, and certainly I'm not doing this classical story justice with this tiny review, but well, it's a really beautiful story that you get classically, so I think it's natural to ask what happens equivariantly. Is there some way of carrying out this story equivariantly? And in particular, is there a nice G equivariant Kn local sphere that fits into a similar picture? And well, that's a question you can ask, and I'm going to claim that the answer is yes, and describing that is going to be the first part of this talk. So you're going to see a couple ways of trying to get at a equivariant Kn local sphere, and the punchline is that they're going to be giving the same thing. So roughly the first part of my talk is going to be this kind of more conceptual side, and in part the purpose is to serve as motivation. Then for the second part of the talk, where I'll talk about some more of the computational side of things. So that's the goal. We want to get at what is an equivariant Kn local sphere, and maybe there's various ways that you could imagine trying to answer this. I'm going to start with a very kind of hands-on, down to earth approach that, well, it uses some high-powered theorems, but it's going to be really easy to get your hands on with going through the Siegel conjecture. So first, let me recall the Siegel conjecture, or I guess before that, I need to recall or fix a bit of notation and terminology. Anytime that you have some, say, non-equivariant cohomology theory, you can treat your non-equivariant cohomology theory as sort of an equivariant cohomology theory by declaring that the equivariant cohomology of some, say, G space is just the non-equivariant cohomology of the Borel construction or homotopic cone of the action on that space. And this is something that you can do with cohomology theories, but really it's a bit better than that. This is really giving you a functor from spectra to G spectra. And well, when it's written in the slides, I'll write this with a BG. And when I'm pronouncing it, I'll either say BG or something like Borel construction. So what is this Borel functor? Well, if you have some spectrum X, then another way of writing this Borel construction on X is you take your spectrum X, view it as a G spectrum with a trivial action, and then map EG into it. But the way that I like to think of this sort of Borel construction on X is more computationally sort of in terms of its coefficients. It's going to be a G spectrum, so you can think, well, what is its, say, representation graded coefficient's going to be? If you take some virtual G representation alpha and map the representation sphere S alpha into your Borel construction, well, what you're getting is nothing more than just the ordinary spectrum of non-equivariant maps for the tome spectrum of alpha into X. And by tome spectrum, I mean, well, alpha is a virtual representation, so it's defining a virtual vector bundle over the space BG, and you can take the tome spectrum of that vector bundle. And well, in particular, this tells you that the, say, representation graded coefficients of BG of X is nothing more than, it's just the ordinary sort of X cohomology of tome spectra of virtual representations. And well, in some sense, so this is a way of getting equivariant cohomology theories, but where the group isn't really doing much. I mean, you're making it into an equivariant cohomology theory in kind of a very simple-minded way. But the Siegel conjecture tells you that despite that, this is really seeing quite a lot of information. So the Siegel conjecture, in the special case that I want to kind of hone in on, states that, or implies that, if you have, say, some P group G, then the G equivariant sphere spectrum is essentially the Borel construction on the non-equivariant sphere spectrum with a trivial action, at least up to a P completion. So if you have some P group G and you're studying G equivariant stable stem, well, most likely the most interesting case is going to be the P primary part. And this tells you that that P primary part turns out to be nothing more than cohomotopic groups of certain tone spectra. And one thing this tells us, or it gives us, is kind of one possible candidate for what you might think of as a G equivariant K-n local sphere. You can always just take the Borel construction on the K-n local sphere with a trivial G action. So this is one possible answer. Maybe I'll call these the Borel K-n local spheres for now. These Borel K-n local spheres, it's very simple to define, but they turn out to be fairly interesting, well-behaved objects. Say a few things about these. One thing to say is that because of the way that they're defined via this Borel functor, BG, which is preserving all limits. And as a consequence, this BG basically preserves everything that I talked about in the classical story. Basically, you say the same thing, but you just stick a BG everywhere and everything is still true. So for instance, this functor BG is going to be preserving, say, the chromatic tower. What's happening here is, well, the Siegel conjecture tells you if you care about the G sphere, then to some extent you may as well look at the Borel G sphere. But now the Borel G sphere is really the limit of these Borel Ln local spheres. And once again, the Borel K-n local sphere comes up when you go from the Borel Ln-1 local sphere to the Borel Ln local sphere. And the main upshot that I want to take from this is that this is telling you that, well, whatever the role of these gadgets are, these Borel-Kane local spheres are going to be seeing a lot of information about patterns within these equivariant stable stems. So they're seeing a lot. You might try to compute them and see what you get. And all the standard methods of computations in chromatic homotopy theory apply just as well here. So for instance, the Borel-Kane local spheres is the homotopy fixed points of the kind of Borel construction on Morava E theory with respect to the action by the Morava stabilizer group. And well, what is this sort of BGEN? It's something that's kind of built out of the e-cohomology of various tone spectra. And well, they may not be tone spectra of complex representations, so maybe you have to work a bit harder if you don't have a tone isomorphism, but it's something that is, you have practice computing things like the complex oriented cohomology of tone spectra. And so you can take fixed points, you can look at fixed points all the way down to the Kn local sphere, or you can look at various finite fixed points. And whatever you're doing, you're going to have things like homotopy fixed point spectral sequences for computing these guys. So this is all kind of formal given the construction and the classical story. One point that I want to bring up that's not completely formal is that, well, so the Siegel conjecture, I guess, is telling you that one way of trying to understand these G stable stems would be to look at the homotopy groups of these tone spectra. And well, maybe if you're like me, you might see that and think, okay, great, we've reduced to a classical homotopy theory question. Now we have a lot of practice answering those. Let's just go and compute it. But you run into the problem where you're taking tone spectra over BG, sort of, you're getting infinite dimensional complexes, and trying to study what happens when you dualize those is fairly difficult. For instance, if you try and run just the ordinary atom spectral sequence, well, you're going to run into trouble just trying to get at, say, the E2 page. However, those issues kind of vanish when you're working Kn locally due to Kn local tape vanishing. So one consequence of Kn local tape vanishing is, so if you take this Borel Kn local sphere and map S alpha into it, you're looking at just kind of the Kn local Spanier-Whitehead dual of the tone spectrum of alpha. But that turns out by tape vanishing to be equivalent to the Kn local tone spectrum of minus alpha. And the precise alpha to minus alpha is not really what I want to emphasize here, so much as the point that these Kn local tone spectra, or just these tone spectra, are Kn locally dualizable. They're acting like finite complexes from the point of view of Kn local homotopy theory. And so, well, this tells you that these objects, these Borel Kn local spheres, are really kind of built from things that look sort of like finite complexes in the Kn local category. So these are some objects that you might study. This is one possible answer to how you might find an equivariant Kn local sphere, but maybe there's something that's a bit unsatisfying about this answer, depending on your perspective. Namely, the Kn local sphere isn't just something that you define to compute. Rather, it's popping out of a really beautiful conceptual story about the nature of the stable homotopy category. In particular, the Kn local sphere really is, like the name says, it's the Bausfield localization of the sphere spectrum with respect to this important cohomology theory, the Morava Kn. On the other hand, these Borel Kn local spheres, well, how did we get them? We looked at the Siegel conjecture and said, okay, what else is there that this tells us to compute? Oh, we can just define these guys and it should be interesting. Just kind of defined it by hand, and it's not clear what is the role of these objects. So, well, can we do better than that? In particular, is there some nice G equivariant Morava K theory, which you can then look at the Bausfield localization of the G sphere with respect to? So that's a question that one can ask. Is there a good G equivariant Morava K theory? And the answer to that, of course, is going to depend on kind of what you're looking for. This isn't really something that has a completely unique answer. So to say what kind of G equivariant Morava K theory I want, maybe I'll take as given the n=1 case. Sort of the type of equivariant theory I want is something like, well, at n=1, we have not just G equivariant K1, but actually we have G equivariant complex K theory. For any group G, there's a perfectly good cohomology theory of, well, complex vector bundles with a G action, or the K theory of those. This is represented by a perfectly good G spectrum of G equivariant complex K theory. And so we may as well take our G equivariant K1 to be this G equivariant complex K theory mod P. So taking the point of view that I want my G equivariant Kns to be something like this. And well, maybe there's something that I should mention about these theories here. Well, if you like, and maybe something that you've noticed so far this time, if you like equivariant homotopy theory because you really like interesting group actions on things, then the stuff that I've been talking about is a bit disappointing because everything that I've talked about has trivial action, and that goes for these as well. If you look at G equivariant complex K theory, the underlying spectrum is just complex K theory with a trivial G action. And well, I maybe want to make the point that this isn't a sign that you're looking at something wrong. It's, if anything, it's something to be expected from this point of view, because what are we trying to get at? We're trying to get at the G equivariant sphere spectrum, and the underlying spectrum of that is also just the sphere spectrum with trivial actions. So maybe it's not so surprising that we want to, or that we'll end up looking at localizations with respect to other theories with trivial actions. In any case, so if we take this as our answer for one, well, what would be the right answer for higher n? Well, to get an idea, maybe I want to look at this n=1 case a bit closer. It turns out that in some cases you can identify this even more explicitly using the Atiyah's single completion theorem. Really a special case of just Atiyah's finite group case. Is the case that I want to focus on. Namely, if you have some P group G, everything's nicer when you have a P group. If G is a P group and you look at G equivariant complex K theory mod P, this is nothing more than this is actually something Borel. This is nothing more than the Borel equivariant cohomology theory associated to complex K theory mod P. Or put another way, in this case, our choice of G equivariant K1 is just the Borel construction on K1 with trivial action. So this is a theorem, and it's a sort of true whether you like it or not. And I want to maybe make the point that this is something that is you should maybe expect is a bit generic. Things that are Kn local kind of like to be Borel. And so I'm going to be extremely vague here. But there's a bit of intuition that one might have, which is that if you have some analog of complex K theory, G equivariant complex K theory, but it's kind of living at height n. For instance, what I mean by analog, I mean something along the lines, say if you look at n=2, then you'd be looking at maybe equivariant elliptic cohomology with enough level structures to make it more like complex K theory. In that case, what you expect is that if you take your equivariant theory and you kind of kill the chromatic elements, say PV1 through Vn-1, then you're just getting some Borel theory on Morava Kn, at least if G is a P group. So this is intuition that one might have, and it might even be a theorem in certain special cases, cases where you sort of say what you mean by G at height n. But well, if you take this, if you buy this kind of intuition, what it leads you to is it tells you that however you're defining your G equivariant Kn, if it's fitting into the same kind of picture as what we had with G equivariant K theory mod P, then it's just going to end up being the Borel construction on Morava Kn, at least if G is a P group. In here, of course, I guess it's never written explicitly, but when I say something like Kn and G a P group, I mean the Kn at the prime P, of course. So this gives now a choice of G equivariant Morava K theory that's fitting into the same picture as G equivariant complex K theory. And what's the punchline? The punchline is now we have our G equivariant Morava K theory. You can look at the localization of the equivariant sphere with respect to this object. But it turns out to be nothing more than what we are already looking at. You're really just getting, once again, the Borel construction of the Kn local sphere with a trivial action. And well, this is not something that's very hard to prove. It's fairly, once you know this fact, it's fairly simple to sit down and prove it. It's not something completely formal about localizing this back to Borel theories, but it's not nearly as hard as something like the Siegel conjecture. Really, the non-formal part of this result is just making use of tape vanishing as the main non-formal ingredient of this. But this tells us that whether we're defining this equivariant Kn local sphere via kind of a manual construction that tells us that we sort of what part of the equivariant stem is going to see, or by this somewhat more conceptual approach that they're really giving the same answer. And so if you ask me what would be the right equivariant Kn local sphere, at least if you're looking at a P group, well, I'd say look just at the Borel construction on the Kn local sphere. So that's the first half of my talk. Now I'm going to shift more into computation. So maybe this is a good time for me to catch my breath and ask if there's any questions.
Yeah, is there any expectations for something like chromatic convergence theorem, seeing the Kn local pieces will recover the original P local spectra in this equivariant setting?
So you do have something that's formal. What you have that's kind of formal is once you know that these...
Oh, the co-free ones is recovered in this way. Yeah, so...
Yeah. So this is not the same thing as kind of localizing with respect to some kind of equivariant En.
I see.
So it's not sort of a perfectly satisfying chromatic convergence, but it's enough of a chromatic convergence to tell you that these equivariant Kn local spheres are in some sense eventually going to see everything.
Yeah, thank you.
Yeah, so well, yeah, this equivalence, it kind of goes both ways. If you like the hands-on construction, then it gives a perhaps more conceptual interpretation of what it is you're computing, and if you like the more conceptual construction, then it gives a way of actually computing it. So, well, moving on, what is there to compute? Well, if you buy into this story, then following the story, what you want to do is you want to first start with something like the Borel theory on Morava E theory with trivial action, and compute that, which amounts to computing the E-cohomology of tone spectra of virtual representations. And this computation should include, well, whatever you want it to include, but particular things like whatever you can get at for the Morava stabilizer action. And once you have that, maybe you'll want to go ahead and descend to various fixed points. And really, both of these steps are rather non-trivial. Okay, obviously the first step is non-trivial if you include the Morava stabilizer action, but even without that, just computing these guys is certainly not trivial. So maybe make a couple remarks about this recipe. First remark is something about odd primes, and well, I'm no expert at what happens at odd primes, but little remark. If the order of the group G is odd, then it turns out that all sort of non-trivial, irreducible, orthogonal G representations are really coming from complex representations. So if you're looking at this Borel theory associated to Morava E theory or some other complex oriented theory, you have co-isomorphisms, and computing this roughly amounts to computing the ecohomology of BG. Well, the ecohomology of BG is something that always shows up here, but at least in this case, that's kind of the main object to compute. And of course, this isn't trivial if you want kind of a full description of the ring structure, but you have ways of trying to get at it, like say the HKR character theory and so forth. So the odd prime case, the input, it gets a little bit simple like this. I somehow wonder if this is telling you not that the odd prime case is easier, but maybe that there's something better than ROG that you should be grading with. Maybe there's something that, well, makes the input just as hard in the odd prime case as in the even prime case. Just a thought. Another remark is I've been talking about all these Borel theories, and the word Borel maybe too many times. You might think that I really like Borel theories, and well, I do kind of, but you don't always like Borel theories. It's not always the thing that you actually want to compute. For instance, say you're looking at this kind of Borel G equivariant Morava E1 theory. If G is, say, a P group, and you're working at the prime P, then the TS-equal completion theorem tells you that this guy is really just the P completion of G equivariant complex K theory. And so, well, why not just compute with G equivariant complex K theory? And then, well, if you want to complete later on, you can always sort of complete later on more easily than you can decomplete. And this way, well, if you're computing with complex K theory, it's also telling you something about vector bundles, and that's always fun. And similarly, instead of looking at these Borel covariant forms of Morava E1 homotopic fixed part with respect to the involution, really you should look at G equivariant real K theory. Maybe just briefly mention that this does have a height 2 analog at least. Well, you should think that from the point of view of trying to get at patterns within the equivariant stable stems, the height 2 analog of equivariant complex real K theory is equivariant elliptic cohomology. So, of course, equivariant elliptic cohomology, the status is not completely sort of in its final form, but for instance, recently Gepler and Meyer have constructed kind of integral sheaves of equivariant spectra, at least in the Abelian group case, which is really the only case that we can hope to understand for quite a while anyway. So those equivariant elliptic cohomologies, well, computationally their role is to fit into this kind of picture. So these are some things to compute. Maybe I want to mention just a selection of relevant computations, nothing like an exhaustive list of relevant computations, but just a handful of things that kind of fit into this story. So a lot of these examples, it's maybe a big wall of text, are really at height 1, and it's because height 1 is always kind of nice, and height 1 is nice because K theory is nice, and that's still true equivariantly. Equivariant K theory is also nice. In particular, Karoubi has computed the ROG graded coefficients of G equivariant complex K theory for any finite group G. And this computation is in the form that, well, in each RO degree, you're getting some free abelian group, and he described the rank of that free abelian group. If you want to go further, you're going to need to get more information about the kind of particulars of what's happening with a particular group G. And it turns out that from this point of view, this kind of chromatic point of view, a really interesting and accessible, well, somewhat accessible family of groups are the elementary abelian P groups. And in particular, say the elementary abelian 2 groups. I want to mention that Hu and Chris, motivated by other questions, they sort of gave some more information about equivariant complex K theory in this case. But now jumping ahead to some very recent things, something of first of a rather different flavor. Gilhill, Isaacson, and Ravenel, they computed the coefficient ring of a connective form of C2 equivariant K theory. And via the C2 equivariant atom spectral sequence, this computation, one thing that you get out of it is you can invert a certain class, and then you get kind of the non-connective version fairly easily. There's a lot of interesting stuff going on with how the atom spectral sequence is behaving. It would be really good, I think, to get a better understanding of the interaction between kind of atom spectral sequence methods and chromatic methods in the pseudo-equivariant context.
Can I add that there's also to that, there's also work of Hannah Kong where she takes that from what amounts to the Adams-Novikov spectral sequence perspective.
C computes C2 equivariant little k.
Right, compute that using the C2 effective spectral sequence.
Great, yeah. So then that should also be stuck on this list somewhere. Yes. So there's a lot of computation going into these things these days, and maybe mention some more. So now mention some computations that, well, I've done. I guess I should say some things that I've done if I'm giving this talk. So I've been talking about equivariant K and local spheres, and well, what's the first equivariant K and local sphere to compute? Well, I guess the first one to compute is the trivial group. But once you've moved beyond that, maybe the first one to compute is the C2 equivariant K1 local sphere. And so I have a computation of the homotopy ring of the C2 equivariant K1 local sphere, following this kind of story that I've been promoting. Sort of start with C2 equivariant, two-adic K theory, and just keep descending down until you get to the K1 local sphere. Another computation, so I mentioned that there's some stuff known about equivariant complex K theory, including for, say, an elementary Abelian 2 group. That work was mainly focused on kind of the additive structure. Well, I was curious about some of the other structure that you see here. So also have a computation of, say, equivariant complex and real K theory with sort of all the additional structure that you would want, like products, transfers, restrictions, power operations, and atoms operations in the elementary Abelian 2 group case. There'll be some very interesting patterns here. I think you're going to get much more interesting patterns in the sort of higher rank elementary Abelian case when you go up to higher theories. These groups are sort of exhibiting some chromatic phenomena that you're not really seeing the full force of if you're just looking at a height one thing.
So can I ask another question? So,
Yeah.
So the answer here to part 5, so that's going to be like at least as complicated as the answer to part 3, right?
No. So in part 3, if you're looking at this is the connective thing.
Oh,
So
I
it's
see.
not that
Okay.
one is
Okay.
more or
All right.
less
Fine.
complicated than the
Okay.
other.
Great. Yeah. Okay.
But
Terrific. Thank you. Sorry,
you
that
have
I missed that
the
point. Yeah. Okay. Thank you.
hard stuff, and you don't get that here, but you do get other hard stuff that you don't see here. Great. Then, yeah, a connectivism would be very interesting, but I expect difficult. Well, everything's difficult. I'm sure there's probably some very interesting patterns that you would see trying to get at that. And maybe finally, we're running a bit behind on time, a couple other computations that I'll mention. So some stuff that is forthcoming, and meaning that hopefully it's out someday. Maybe there's other forthcoming stuff that I don't even know about. One is a computation of Bonaventure and Stapleton. They've computed sort of the zero stem of the localization of the G sphere with respect to G equivariant complex K theory for G and odd P group. And this is a very nice little thing because it's not a K1 local thing. It's something that's really integral. There's no completion here. And then I have some computations that are the computations are done, but the writing isn't of some more stuff in the C2 equivariant case. For instance, the Borel C2 theory associated with Real Brown-Peterson homology, or C2 equivariant TMF03 and some of its friends. But something that you might notice from this list, or at least from my contributions, is that
William, do you have the computation of TMF03 C2 equivariant listed? Like, have you written down somewhere?
I have things. Yeah, I have.
Okay, please forward me after the talk. Okay, thanks.
Yeah, I don't know if I have something written down that's readable by others quite yet. At least not digitally.
Okay.
Yeah. So, what was I saying? Yes, as Dan Isaacson puts, the forthcoming in scare quotes. Now, I expect that it should be out in not too long. If you email me, then I can say you can get me to write something down. Anyway, so I went to, so where was I? So the group C2 is very interesting, and maybe I want to wrap up by just saying a few sort of kind of getting into this group C2 and just pointing out the sorts of things that you see when you're doing kind of the C2 equivariant computations. So here's a picture. Gotta have a picture. This is a picture of C2 equivariant real K theory, and well, what's going on in this picture? This is not a spectral sequence chart. This is a depiction of a bigraded object. So what's going on here is these black dots are copies of the integers, and the orange dots are, well, copies of Z mod 2. The way that I like to index these charts is that the horizontal axis, kind of the x coordinate, is the total stem or total degree, and the vertical axis or y coordinate is basically how many copies of the trivial representation you have. And the reason that I like this kind of representation has to do with these blue lines that you're seeing here. So these blue lines are indicating multiplication by the Euler class of the sign representation, which I'm in the honestly rather bad habit of calling rows. These are multiplications by this Euler class row. And the reason that I like this sort of depiction is, well, if you take this Euler class and you take the colimit along it, that's giving you the geometric fixed points, the geometric fixed point spectrum. And so if you look at this bigraded thing, what's happening is each column is kind of living over a particular stem of the underlying spectrum, which you can even identify as sort of a cofiber of a row, whereas each horizontal line is living over a particular stem of the geometric fixed points, invert row. And this bigraded object is kind of sandwiched between these two things as some kind of gadget kind of deforming these. So that's how the picture's set up. What's in the picture? Well, maybe the most famous class here is right here, this eta C2. This is the C2 equivariant Hopf map. So the C2 equivariant Hopf map is detected by C2 equivariant real K theory. If you look over here, there's a -2 under that blue line, and that's telling me that rho times this class is -2 times that class. In other words, rho squared times the C2 Hopf map is -2 rho, a classic relation. But this is a very interesting kind of relation. Well, what is this relation telling us? It tells us, for instance, if we go to the geometric fixed points, that's basically set rho equal to 1. The fixed point of C2 Hopf map is -2. On the other hand, well, this C2 Hopf map is kind of lifting the classical non-equivariant Hopf map. It's an equivariant refinement. And so this relation says that, well, the Euler class is somehow connecting -2 with eta. And if you'd like, you can think of -2 as kind of a chromatic height 0 class. And eta as like a chromatic type 1 class, and you get this kind of transchromatic type of relation. And this turns out to be, well, fairly generic. The order class is always going to be giving very interesting sorts of transchromatic relations. This case of KO theory is kind of the simplest case where you see some interesting stuff going on. And when you go on to higher, more sort of higher chromatic objects, you're going to be getting relations, transchromatic relations at higher chromatic heights. Maybe I'll say that this relation sort of in the lingo is encoding something about Mahol invariance. Maybe I don't want to say anything about that for sake of time. One other thing about this picture that I didn't say is there's some lines that are dashed. These are just some multiplications that are hidden in the homotopic fixed point spectral sequence when you go from KU to KO. So I think I have time for one more slide. I want to say a little bit more about C2 equivariant homotopy theory. So a lot of work in C2 equivariant homotopy theory and also bootstrapping from C2 to other groups has to do with kind of the real equivariant story. So there's something that I want to note, which I kind of commented on before, is that if you look at something like C2 equivariant KU, well, the C2 here is not the same C2 that acts on complex K theory by complex conjugation. The C2 equivariant KU just isn't at all the same thing as, say, a T as KR theory. And well, a priori, there might not be much of a relation between these, but it turns out that there is a very close relation between these. So and this is proved in the sort of Gilhois and Ravenel's paper. In the connective case, for the non-connective cases, sort of the same thing. If you look at the C2 equivariant Hopf map, well, this is detected in C2 equivariant KO theory, and if you then kill that, what you're getting is, well, KR theory. And this is kind of an equivariant refinement of the classical Wood equivalence, where if you take KO and you kill eta, you're getting KU. This is a really nice equivalence. It's telling us some good things. One thing it tells us is that from the point of view of looking for theories with an interesting equivariant Hurewicz image, well, something like KR is kind of not the place to look. KR is like you take C2 equivariant KO theory, it has a modest but interesting Hurewicz image, and then you sort of kill all the interesting parts. Sort of kill everything that's seeing good stuff like Mahol invariance, say. Another thing it's telling us is that, okay, so classically, if you take KO and you kill eta, that's giving you KU. And one consequence of this classically is that because eta is nilpotent, the Bausfield class of KU is the Bausfield class of KO. Whereas in this case, well, C2 equivariant eta is rather famously not nilpotent. And so you don't get that kind of equality here. Instead, what happens in this case is, well, if you look at the Bausfield class of C2 equivariant KU, that will be the Bausfield class of C2 equivariant KO, but that'll be strictly smaller than the Bausfield class of KR, which in turn is strictly smaller than the Bausfield class of C2 equivariant KU mod 2, or C2 equivariant K1. And well, there's been a lot of work on what are interesting Bausfield localizations of equivariant spectra, which I'm not going to get into, but just want to say that this is a nice picture of what happens in this one particular case. Kind of the KR, the real equivariant case, is sort of sandwiched between the actual equivariant case and the K1 local case. And so this theorem where if you kill off C2 eta, you go from C2 equivariant KO to KR theory, turns out to not really be special to kind of K theories. It's a fairly generic fact about how these sorts of theories behave. For instance, say instead of looking at KU, you look at another thing that's kind of like KU, you look at periodic complex cobordism. This also has a C2 action by complex conjugation, and you can take the homotopy fixed points with respect to that action to get, I just want to look at the ordinary spectrum. If you then take the kind of Borel constructs in the ordinary spectrum, this is going to be detecting some class, which if you kill that class, it's giving you the actual real equivariant form of periodic complex cobordism. And likewise, if you take something like C2 equivariant TMF03, this is going to be detecting some class that you can kill to get sort of the real equivariant TMF13. And really the proofs of these, once you have those classes, the proof is always sort of the same as the height 1 case. But it's telling you that you always get this kind of thing where the real equivariant case is sort of what you get when you're sort of killing some of the most interesting parts of the case with the trivial action. But I think I'm out of time, so this is a good place for me to stop. I'll stop here.